Thanks for the invitation and welcome to the seminar. I'm Baxi Chong from Georgia Tech. And here I will briefly introduce our recent work on the mechanical intelligence in locomotion from information theory to mesoscale robots. I'm the first would like to introduce why information theory and why mesoscale robots. But before I do that, let me first show you a very cute video. Our dearest friend, dogs. Dogs and agile terrestrial locomotors. They can do multiple terrestrial tasks. They can climb the slopes and jump the hurdles, do the hurdles, the hurdles, the hurdles, and hurdles. The slopes, down the slopes, and this is very impressive, the obstacles. And then the hurdles, a sharp turn, and the turns. It's quite impressive what a dog can do. And inspired by this, our quadrupedal robot also achieved remarkable performances on complex terrains. However, those quadrupedal robots typically require some weight and calculations to estimate the terrain challenges and to make the appropriate responses. Here, we will review such calculation-enabled intelligence and the computational. Training such computational intelligence can be time-consuming and challenging. Further, such computational intelligence typically cannot be generalized across different behaviors or in different environments. For example, the quadrupedal robot having a hard time going through the entangled materials. And if we want the quadrupedal robot to carry some payload, the speed substantially slows down. Here, the robot is carrying the weight approximately 1/2 of the body weight of the robot. The quadruped robot also having some troubles going through the obstacles over the slope. And finally, the quadruped have a hard time rolling over. So it has to fold their legs and kick, which takes them a long time to self-right after getting kicked over. So what's all that about? Well, one hypothesis is that the dogs are not good at those behaviors in the first place. They get tripped and they fall. Just for fun, let's play some cute videos of dog videos. Although they might be just playing for cute. But formally speaking, every species has its own ecological niche. That means dogs, or as humans, we are not born tree climbers or grass swimmers. However, that does not necessarily mean that we cannot climb a tree or cannot swim in the grass. We could, but there exist some other animals with a different morphology that are better tree climbers or grass swimmers than us. I was trained as a biophysicist specialized in arthropods. I can give you a bunch of examples where those critters can do much better than a dog. And here's a centipede, navigate in complex terrains while being largely blind. And we also have the ants that can carry the payload 20 times heavier than the body weight. And we also have a caterpillar moving around, perhaps not knowing what's in front of them at all. And finally, this is my favorite, a centipede can perform this dynamic and agile rolling behavior. See, rolling. It's quite impressive what animals can do. And inspired by this, we built a centipede-like robot going through the entangled concrete jungles. And we also have a 2 degrees of freedom robot carrying the payload 3 times heavier than the body weight without losing speed. And we also have a caterpillar robot climb the tall obstacles 3 times higher than the body height. And finally, we have a centipede rolling over and over. So these are what we call the mesoscale robot. Before I go on and on about the control and information theory, Let me first answer the three most important questions. First, what is the mesoscale robot? What is so special about it? And second, who cares about mesoscale robots? And finally, what makes the mesoscale robot so difficult? So first thing first, what's so special about this robot? So if we weigh those robots have approximately 1 kilo, which is substantially lighter compared with a state-of-art robot. And here is a recent literature review of the robot mass and velocity. And we notice that there is a huge research gap for less than 1 kilo. Of course, if we go further down, we will have a micro robot. So we take the name of mesoscale robot as the intermediate between a microscopic robot and a macroscopic robot. So let's take a look at what the state of art of mesoscale robots. We have the Chipaka, we have the Tekens, and we have very here the local, the mini Chong. And despite how cool this robot are, these robots were rarely tested in the environment as complex as those for the bigger ones. And even the name suggested that these are the cups or the mini version of their bigger brother. And it is stereotyped that the mesoscale robots are supposed to be less capable because we cannot afford good motors or good sensors within our weight budget of 1 kilo. So what are we going to do about that? Well, here is where we are at over the diagram. We have a centigrade robot going through the lab robust strings with size variation approximately 20 centimeters. We also take the robot outside and test it over the rocks. The size of the rocks is approximately 30 centimeters. And finally, we take the robot into the grass, the slopes, the 30-degree slopes, and we achieve reasonably good performances. So as you can see, our goal is to develop the mesoscale robot as capable as those for the bigger ones. But who cares about the capability of the mesoscale robots? The first application would be the CBRN threat detection, short for chemical, biological, radioactive, and nuclear threat detections in the confined spaces such as the collapsed buildings or disaster scenes. Here is an example of the collapsed buildings. And for the robot to go inside those buildings, those holes or the tunnels are too tight for large robots. And further, we don't want to have the large forces on those loose materials, which can collect the further collapsations. So we want a lighter robot for the minimum invasive inspections. However, to go inside those places, we still need to overcome those two obstacles, which are too large for the state-of-art mesoscale robots. The second application would be the agriculture, where there is a huge market for automation. The state-of-art agricultural robots are mostly wheeled and big ones. Their application is limited or specific to the seasons, field conditions, and crop type. Because if you're not going to be careful, those robots will crush your crop. And despite how efficient those robots are, there is still a need for the precision agriculture. That means we want to inspect each of those crops for the weed removals or for the disease detections. Here's a concept map. But to do that, we still need our robot to go in around those crops, this farmland. And here is a picture of farmland. It's a mixture of different terrestrial challenges. In other words, there's also a need to develop a mesoscale robot that can run in the farmland. Mostly on this topic, on this application, I have a startup company with my current advisor Benjamin to provide the mesoscale robot solutions to agricultural precision. And finally, there are actually more applications if we can support those light and efficient locomotion. And here is a cool demo by the tier of smart players. So instead of reaching out to a table, the table walks to us. And despite how cool this video is, demo is, this is not my home. This is real. So even an organized home can contain some indoor clutters. In other words, there's also a need to develop those mesoscale robots capable to move over the indoor clutters. Okay. So we have developed those needs for the mesoscale robots. But what is stopping us? What are the essential challenges for the mesoscale robots? It all comes down to the sizes. So here are the three pictures of the same corner in Georgia Tech, viewing from different perspectives. Now let's for fun define a number. The number of active substrate objects during locomotion. And now imagine if we are big. We'll simultaneously interact with more than 100 objects. A number that is large enough so that we can consider the substrate as a continuous medium. And this has been a research interest for my current advisor and his first student, now Professor Chen Li. And now if we are small, everything would be big for us. But we only need to interact with one object at a time. So now consider if we're intermediate. We are simultaneously interact with about 10 objects at a time. Everything is complicated and entangled. And it's a complex system, and it's likely the noise is inevitable. There is a lack of model to develop reliable locomotion in the noise-dominated regime. And that is what I'm talking about today. That is my research topic. This leads us to the overview of my talk. And I will first talk about reliable locomotion in noise-dominated environments. Okay? So noise-dominated environment. Speaking about locomotion, and if we consider locomotion as movement of matter, it has a rich history, dating all the way back to Aristotle, who stated that all moving objects eventually come to rest unless an external power continues to move them. Of course, it will prove it wrong. In Newton's law, the importance of inertia is highlighted. And it is the inertia that facilitates the trains and tracks, the cars and roads, the most effective and most efficient method to transport mass in our modern society. So let's take a different look at those inertia-driven locomotion. There are two essential properties. First, theoretically, there can be infinite displacement per unit force because it's inertia. It's efficient. However, such efficiency relies heavily on the homogeneity of the landscapes. Any perturbation would cause substantial delay. So therefore, we cannot have inertia-driven locomotion in noise-dominated environments. And to counter the terrain heterogeneity, people propose to take steps. By taking the steps, we essentially discretize the locomotion. In other words, there is an upper bar about this displacement that you can get per step. However, we got to choose where to land our feet, and offers a way to counter the environmental heterogeneity. And that being said, it has been stereotyped that the computational intelligence, the capability to perceive and respond to environmental perturbation, is a necessary condition to facilitate step-driven locomotion. we wonder if that is universally true. And here is one of the examples of legs. The third pair of legs can avoid us from the catastrophic failures like loss of stability. However, these robots still suffer from the minor failures such as the thrust deficiency. That means, given sufficient time, the robot will still move from A to B. But the arrival time is indefinite. The punctuality is questionable. And inspired by the success of just having one more pair of legs, we wonder what would happen if we can have more legs. And here is an example of a 12-leg robot moving on pebbles with size variations approximately twice the height of the robot. It moves just fine. Whereas its 6-leg version is not going anywhere. We then take the robot inside and test it over different indoor clouds. We have the levels, the slopes, different surface frictions, and the lattices, and finally going through the top obstructions. So everything on this video is operated in an open loop manner. In other words, we observe an emergent advantage of having more legs. But is there a way that we can say something about the principle of locomotion that includes those morphological redundancy? Well, this is a complicated question, and to gain more insight, we take a step back and learn from information theory. How can we transmit signals over noisy channels? Well, there are many ways to transmit signals over noisy channels. First, there can be continuous analog signal, which in principle can convey infinite amount of information per length of signals, because the first derivative, second derivative, etc., etc., etc. However, the continuous analog signal is very sensitive to channel noise, and the recovered signal can contain some errors. It's very similar to inertia-driven locomotion. And people also propose to digitize the signal transmission into bits. And in doing that, there is an upper bar about information that can be carried per bit. Very similar to step-driven locomotion. And there are two ways to facilitate digital signal transmission. The first is a retransmission channel. The source emits a signal, transmitted, get contaminated, and the receiver detects if the signal contains some errors. If there is, it simply requests another one to be retransmitted through the retransmission channel. The feedback systems are similar to computational intelligence in step-driven locomotion. And Shannon argued that we don't need a retransmission channel. Instead, the coding redundancy is sufficient to drive reliable signal transmission over noisy channels with error rate arbitrarily close to 0. So we learned a principle about reliable transportation without feedbacks. Now we wish to generalize this principle to locomotion. In other words, if each of the locomotor is sufficiently complicated and redundant, so it's many links, can it just go without any feedbacks? And to make this argument, of course, we need to take a quantitative connection from locomotion theory to signal transmission. Let's first take a breakdown of signal transmission. To transmit a signal, we first need to encode the messages. How do we go from ABCD to the binary bits? Just for my amusement, here I show the Morse code. And here, the desired, the transmitted bits are transmitted over the noisy channels. And it gets contaminated. And we estimate the message over the decoder. And Shannon told us the estimated message W dash can be arbitrary to W, our original message. Here, to make our argument, the key insight is to make a quantitative connection between a bit and a step. And we need to model a step as our discretized thrust input. Let's see how it goes. Here we have a locomotion task. The robot needs to go from A to B over some distance B. And to go there, we design some spatial and temporal distribution of steps, telling us when and where should we make a contact. But as the robot implements the stepping patterns, it can get contaminated. And actual stepping patterns can contain some noises. So our end goal, our game, is to argue that the actual destination, D dash, should be arbitrarily close to D, our original destination. To make this argument, there are too many questions that need to be answered. For example, the steps of forces has a unit of Newton. The length, the destination has a unit of length, has a unit of matter. But how can we encode the destination into the stepping patterns? What is our Morse code here? Well, we have one hypothesis. Here, we put this robot on different slopes and directly measure the relationship between the thrusting forces and the actual velocity. And after some evaluation, some modeling, we notice that there exists a linear relationship between the thrust and the velocity. So this linear relationship can allow us to map the perturbations of stepping patterns into the actual destination. So then clear our question mark here. So now, if I look at our hypothesis, reliable locomotion with sufficient redundancy. But we haven't defined the redundancy yet. What are our redundancies? The first redundancy we considered is the temporal redundancy. That means trial and error. That means if we fail to reach our destination within the first second, we repeat it and we repeat it until we make it. Trial and error. So of course, the temporal redundancy is evaluated by the T, number of cycles. The second redundancy we considered is a spatial redundancy. Instead of repeating all those steps temporally, we repeat all those steps spatially. That means at each instantaneous time, there are multiple steps simultaneously interact with the terrain. The advantage of spatial redundancy is that any perturbation on a single step will be shared by the entire robot. In other words, spatial redundancy will serve as a mechanism similar to moving average filter against the environmental perturbation. So of course, the spatial redundancy is evaluated by the N, the number of legs. So we have defined the redundancy. Let's finally define the reliability. To do that, let's take a look at our simulation results. The y-axis is the actual destination after t periods. The x-axis is the time. The shaded area is the 90% of confidence interval of actual destination. Let's first take a look at the blue curves. Both the average and the variance grow as a function of time. So that means if you wish to go 10 units of destination, if we are lucky, we could go there within 10 seconds. But if you're not lucky, we have to wait until 30 seconds. That means for the temporal redundancy, we can only guarantee the completion of locomotion task, but we cannot guarantee the punctuality. But then we look at n equals to 8, at 8 pairs of legs. In those cases, the error bar are tightly bounded. So this leads us to a hypothesis that with sufficient spatial redundancy, it can not only guarantee the completion of a locomotion task, but also the punctuality of a rider. And here is our formal statement. Reliable and predictable non-inertial locomotion can be probably generated by noise, local terrains given sufficient spatial redundancy. Notably, our statement is philosophically in line with Aristotle, the force-dominated mass transportation. So enough of the statements. Pocket shape should be the robot. Here is our robot. We have all these robots from 6 legs to 16 legs. And we record the time required to go 60 centimeters. That is y-axis, the arrival time. The x-axis is number of legs. And we notice that on flat terrain, it's not much of a difference. Right? Then we challenge all those robots on complex terrains. And the advantage of having one x will be much. If we are lucky, like the first time, the robot will be just fine. But the robot will get stuck easily, like this. We're seeing right now, it will get stuck easily. Whereas the 16-leg version will have a consistent velocity output. It is also evidenced by the robot. The lower bar doesn't change that much. But the upper bar of the arrival time substantially decreased as a function of number of legs. And the math told us that the upper bar and lower bar will converge to a single point. And that is our guaranteed locomotion. That means if we wish a robot to go from A to B in 10 minutes, the robot will go from A to B in 10 minutes sharp. So within this framework, we have developed a baseline for the reliable locomotion in noise-dominated regime. However, it's still far from real applications for 2 reasons. First, it is slow. Second, we need far too many legs for the practical sessions. How are we going to address that? Oh, this leads us to the second part of my talk today, the control architecture. Before my presentation, let me ask you a question. If we wish to have higher speed or longer stretch, do we want a longer legs or more legs? We typically want a longer legs. But can we improve the speed with many legs? So this will be the research topic of my second half of my talk today. And to answer that question, we really need to ask ourselves, do we really understand the robot with redundant structure? As we make a robot more complicated, we have to deal with the high dimensionality. It's a good thing and it's a bad thing. It's good because we have a larger space to explore. It is bad because we lose our intuitions. And we have to rely on some dimensionality reduction tools, like templates. But so in this way, the additional legs can only contribute to the stability or the robustness, and not helping us with the agility. So here's a stereotype. The agility goes with robots with fewer legs, and robustness goes for a robot with many legs. If we wish to improve the speed or agility of the many legs, we really need to embrace the high dimensionality. Is there a framework that we can design effective fits over the large dimensional space proposed by the many legs? Well, coming from a physics department, this is my PhD thesis. The short answer is yes, we can. So let me show you how. So this framework was originally proposed by Purcell and Wilczek, the particle physicists, the Nobel winners. They argued that at low Reynolds number, the displacement will exclusively depend on the shapes of shape changes, not the time. And they showed this through the example of a thrilling swimmer in an idealized fluid. And 20 years later, my current advisor, another advisor, Professor Howie Joseph, showed that we can extend this framework from an idealized fluid to a practical robot, the thrilling swimmer robot. And he identified a function where we can optimize for the sequence of shape changes that will give us the best displacement. And now we wish to use this method to understand more complicated behaviors, such as the snakes or our centipede. But we hesitated because the snake locomotion seems to be fast. Is it really okay that we can use a framework originated of life at a low renal zone? Or more importantly, can we identify a number to quantify the importance of inertia in a terrestrial locomotion, similar to renal zone? Following this idea, we have defined this coasting number. It's defined as the coasting time, the time after the locomotor stops wiggling, the complete stop. Time duration is what we call the coasting time. If we normalize this time by average between speakers, it is our dimensionless number, coasting number. And notably, in the business report, our defined coasting number is related to the subject the ratio of the density of the fluid and the density of the total. One clear advantage of the coasting number is that it can be easily generalized to the terrestrial locomotion. And here is a list of all the coasting numbers that are in the systems that we studied. And we notice that it's well below 1, allowing us to safely ignore the inertia, at least for now. So knowing that inertia doesn't matter, at least not much, we can look at the sequence of shape changes and then apply geometric mechanics. And then as a result, we can enable the snake swimming those granular media. But we're looking at the legs. So now let's look at the legs. Here is a leg swimmer. The legs make things complicated because the shape space is now in a more complicated manifold cylinder. We spend a lot of time explaining geometric mechanics to those non-Euclidean topological structures. And now, as a result, we can enable the sand swimming in quadrants. And then finally, of our topic, this is a centipede. This is fast, and we want that to happen on our robot. But this robot has a more complicated topological structures. It's a torus. After spending a lot of time, we can calculate the terrestrial swimmers in the centipedes. And if we compare this 12-leg robot swimming to a bipedal movement, we immediately notice that the thrust generation mechanisms are different. For bipedal, it's primarily legs. The legs contract and retraction with the ground to generate forces. And for this 12-leg, 12 terrestrial swimmer, it seems to be the body undulations. If we circle back to our original question, how can we improve speed of from the many legs? We have one hypothesis. It is the body undulation that do the job. And to test this hypothesis, we construct a performance space. X-axis is the amplitude of leg movement. The y-axis is the amplitude of body movement. And here are the 3 sample points across the performance space. Left panel, pure body undulation. Right panel, pure leg movement. The intermediate is somewhere in between. By comparing all 3, already notice there is an advantage to use your body. And here is what we sampled the entire performance space and obtained a heat map. And we notice that the optima emerges to be the pure body undulation. And this is a conclusion that we have from a 16-leg movement. What would happen if we have 8 legs? Well, the optima seems to be different. And if we sample the entire performance space, we notice that the optima is somewhere in between the body and the leg. So this is quite interesting, that as we decrease the number of legs, the optima shifts from pure body undulation to somewhere in between. And we further quantify this observation by sampling all those different robots and we work their output. There exists a smooth transition from pure lead in the hexagon to a pure penetration in the 16 volt. So if we circle back to our original question, how can we use the additional legs to improve agility? We at least have one solution: use drop body. So now we agree we can use the additional legs to improve agility. We can also use the additional legs to improve the robustness. Can we simultaneously improve the robustness and the agility? That will solve our problem. To do that, let's take a different look at our leg-driven motion and look at the mechanisms for the robustness. We notice that all the legs are doing exactly the same task. That means there's redundancy in grunt reaction forces. It's very similar to simple repetition in signal transmission. And upon challenge by the boundary terrains, the gravity will redistribute the reaction forces. The gravitational responses serve as the majority load decoder. So of course, these robots will have reliable and robust performances on the boundary terrains. And now, what about the body-driven movement we just identified? So here, all the legs are doing different tasks. There's no more redundancy in ground reaction forces. So of course, the speed is very sensitive to the terrain heterogeneity. So for the same robot, we can have this trade-off between the agility and the robustness, depending on our control and even the open loop control. And there exists a spectrum between the agility and robustness. Let's take a look at our experimental results. The y-axis is the speed, the x-axis is the spatial period to characterize the relative body lag usage. The red curves is our experimental results on the flat ground, and the black curves are the experimental result of bumpy ground. They have the opposite traits. So this has the flavor of computational intelligence. And how about we adaptively choose the spatial period depending on our estimated terrain complexity? To do that, there are many ways to do that. We need a camera. Yes, we can. However, remember, our goal is to reduce our weight object. So we choose to use those very simple and light contact sensors, which can tell us the actual stability particles. And by comparing the actual stability particles to our desired stability particles, it can be used to estimate the terrain complexity. And therefore, we designed this very simple linear feedback controller as our start game of computational intelligence. It turns out that this very simple and naive computational intelligence can not only help us to improve the speed, it also preserves the feature of guarantee. Because we all know that the linear controller has proven stability in dynamic systems, right? So how can we interpret these results? Especially in the broader spectrum of computational and mechanical intelligence. And to answer those questions, let's take a step back and appreciate the great work of Cassie. As we've discussed before, the field-like systems, the complexity is in the real-time detection and responses in a software design. And by proposing redundancy-based framework, we essentially transferred the complexity from the computational intelligence to the mechanical intelligence. Now, if we compare our robot to a Cassie robot, despite the dramatic difference in the distribution of intelligence, we converge to a very similar absolute speed. So that means there might be it indicates that there might exist some equivalency between the mechanical intelligence and the computational intelligence. And to quantify this, we propose a control architecture, the CI and MI, and to evaluate, to systematically explore the trade-off and the equivalency between the computational and mechanical intelligence. So we made a bold argument that there exists an upper bar of a velocity given terrain with no complexity. It is approximated, can be approximated by the mechanical intelligence complexity plus the computational intelligence complexity. And this upper bound is very similar to the entropy in signal transmission. And we did some preliminary work to quantify those relationships. We have a 12-leg robot feed forward without any feedbacks, has similar level of performance of 8-leg robot with some feedbacks. So let's circle back. The mechanical intelligence in our systems is sort of easy to quantify. We can just count the number of legs. But how can we quantify this computational intelligence? And before I answer that question, let me show you some examples of how computational intelligence can help us to improve the robot performances. We have a baseline, a 12-leg robot, feed forward, no feedbacks at all. Then we design a single input, single output controller with sensors operating at 0.1 Hz. And we notice that there's a slight improvement. Then we wonder what would happen if we increase the sensor bandwidth. The operating at 0.2 Hz, we get a much better performances. And then we wonder, why we have to limit ourselves to a single input, single output controller? We can design a multiple input, multiple output controller that can also substantially improve our performances. So this leads us to further decompose the computational intelligence into the sensor complexity to the controller complexity. So this is our hypothesis. First, in future work, we will explore this relationship more systematically and decide the theoretical values. This equations, this hypothesis will help us to build mesoscale robots and telling us what to sense and how to respond to save on our sensor budget. So in the previous section, in this section so far, we've discussed how do we save on the sensor budget. Let's wrap up on how do we save on the motor budget. Do we really need those motors, this robot with that many motors? And to answer that question, let's circle back to our original question. Do we really understand the robot with redundant structure? The high dimensionality associated with robot with many legs is largely underappreciated. Let's for fun ignore all the joint angles and only look at the binary contact sequences. And we notice that for robot with n legs, the total number of contact sequences is 2 to the power of n. Right? And this is not scary yet. But if you look at the total number of contact state combinations, it's a huge number. And for robot with 6 legs, this number is 2 times 10 to the power of 89. But this number is largely underappreciated or never explored because who cares? Most of those contact sequences are not going to be useful. But how can we know a priori that those sequences are not useful? Well, we have a hypothesis. We have intuitions developed from bipedal quadruped. So in this last section, let me wrap up by exploring the full contact state sequence space And in doing that, we will learn how do we save our budget on the motors. First, we need to connect the contact changes with locomotion. There has been a rich history in locomotion without contact changes. One of the recent conclusion is that if there's no contact change, there will be no locomotion. So this will help us to relate the contact changes to locomotion. So we can use a graph method to define the vertices as the contact particles. A robot with 6 legs, its number is 64. It's not scary. We can also define the edges as the net displacement resulting from the contact switch. So in this way, we can simplify this contact design problem into a well-defined problem in a graph in a discrete map. And it's solvable. Before I show you our experimental results, let's first show some intuitions from bipedal quadruped. For bipedal quadruped, the left and right movement is very symmetrical, such that the counterclockwise turning from my right-hand side movement is balanced by my clockwise turning my left-hand side. So the robot turns approximately the same amount clockwise and counterclockwise. But as a result, the very symmetrical gates only operate well over the probability. It's not super effective compared to gates. But when we compare it to our optimized gate from the graph, we notice that the robot is not symmetrical at all. And the robot turns clockwise for 3/4 of a cycle and rapidly counterclockwise for 1/4 of a cycle. And this robot accelerated at higher temporal frequency. It's because the inertia is upfront here, stabilizes the unstable configurations. Longer discussion, but you'll have to trust me. Okay? So we have identified a gate that is suitable to operate at higher temporal frequency. But beside that, what else do we need? Let's take a look at those gates from the graph. And let's focus on the 2 motors pointed by the arrow. We'll notice that those 2 motors never move, never rotate, never activated throughout the entire gate. That means we can simply replace those 2 motors with a rigid connection. We can save our weight budget on the motors. We can remove those 2 motors. And importantly, let's take a step back and learn from what we discovered. We started with a quadruped. And now we add 2 more motors, hope to improve their speed. And now we are saying we can remove 2 of the motors while achieving the same forward performances. These 2 robots have the same number of motors. And robot on the right-hand side is a robot specialized in forward moving. So there is an advantage to go through the dimensionality expansion and reduction and convert to a more specialized robot. So what about other robots? For a sidewinding robot, can you guess which leg can we cut? Any guesses? This one can be cut by the rigid connection. And what about the load carrying robot? Which motor can we cut? I guess everything can be cutted except for the body duration. So more systematically, here is we map the locomotion problem into a graph problem, right? Discovered. So instead of finding the path in the graph, we are also interested to explore what would happen if we delete the vertices and add some new ones. That is a real value and provide guarantees to cut our weight budget for our mesoscale robots. So with that, I'd like to wrap up my presentations. Thank you so much, and I will play this video. Thanks.
Well, we can take questions.
Very beautiful perspective. I'm trying to understand the mapping between standard channel coding and multi-legged robots that you talked about. So you said that the terrain is the channel. The morphology is the source code. And the controller is what?
So yes, the terrain entropy is the agent of noises, right? And our motor is how do we coordinate the robot? It's the it's a robot morphology, and also how do we coordinate stability. So those are our codes. And then this code get contaminated by the interaction with the optical or with the complex terrains gets contaminated. Our goal is that despite the stepping point is contaminated, we still reach our destination if we have the many legs.
And so, where does the dimensionality of the robot come into play? Is it the larger the number of dimensions, more the redundancy in the original code words?
That's excellent. Yes, so the dimensionality will play a role here. So if every leg is repeating the existing legs, right? So we're just simply repeating, consider a 10-leg robot as 5 repetition of a 2-leg robot. So there's a dimensionality reduction, and this dimensionality reduction can help us to improve the robustness because there's redundancy in the ground reaction forces. And we're also interested in some other dimensionality reductions that can improve the agility. So the real trick here is to how do we smartly choose between different dimensionality reduction tools such that we can allow us to adaptively choose between the agility or the robustness depending on the structure. Does that make sense?
It seems like because there is the dynamics of the robot, which introduces temporal relations between the next state and the past state. And whereas in standard coding, there is no such dynamics. It is the channel operates blockwise. So it's a little confused about like the analogy.
Yeah, so here we assume that everything is independent, so the temporal does not correlate. So in this model, we will prove this analogy. We assume that what happened right now will not affect happening in the next second, the next step. We assume every step is purely dynamic, just like this Gaussian distribution. Similar to those Shannon's assumption on the noises from the channel.
Early on, you were talking about the some of the gaits of animals being different topologies. Can you explain like what topologies are or something?
Yeah. So for the snakes, we're dealing with so these snakes, consider a snake as a, for example, 100 link string, right? But for each link, it's the same kind of joint, right? Every link is sort of perform the same role in the motion. But for lizards, they have different types of joints. Some joints are the leg joints, some joints are body joints. So if we wish to introduce the dimensionality reduction, we have to counter for the fact that there are different types of joints. To model that, we need to nonlinear dimensionality reduction, which includes some manifold learning. Therefore, we converge to a cylindrical coordinate for a lizard legs and torus shape spaces in centimeters. It's the different types of joints. Yeah, for the centipede, there are joints to lift legs there are joints to protractions, there are joints to body undulations. But for the snakes, it's purely lateral body undulations. It's not model. So that's these images.
I have a question. So in the beginning of your talk, when you were talking about redundancy, kind of providing a upper bound to the kind of velocities you can achieve, is that also dependent on the quality of the terrain? So you only showed examples of walking over rocks. If it was mud or, something closer to liquid, like a viscous liquid.
That's exactly, so that upper bound, this upper bound is only a function. It's also a function of the terrain. Yeah.
Okay.
So of course, on the flat terrain and on the bumpy terrains, we will have the same different upper bound. So it's also a function of the terrain.
All right, I think, did you have a question?
No, I think I'll email you. I do have several questions, but I need some time to go through all of this, okay?
What's it?
So I felt like you introduced redundancies to morphology, then you used control and then reduced it, isn't it? Because I know, I designed, I had a project where we built a quadruped with central parking generators, and there were advantages over the different controllers. So I feel like changing the controller rather than introducing the redundancies only to affect them again would have been an easier solution.
That's excellent question. So it's central parking generators, those are the decentralized.
Yeah.
So we're talking about the centralized structure. So actually, there's a equivalency also between the decentralized control and the centralized control. Right? So of course, you can improve the performance by changing from fine-tuning the CPG and also the coupling string, for example.
Yeah.
One of our concurrent studies do that. The CPG can work better if you can have some centralized guidances on how do you better adapt by changing the coupling string, stuff like that. So yes, so that's one thing. But remember, this is computational intelligence. So we're talking about the mechanical intelligence. So what if there's no sensors at all? What if in those dark rooms or in those collapsed buildings, there's no sensors, the sensors are not reliable? In those scenarios, perhaps it's also a good, it would be one at least alternative solution to provide robustness just by the mechanical intelligence.
The question was, and the efficiency, there would be a point where you introduce additional legs that would, so the additional legs are reducing the efficiency. There is a cost to that eventually. Is there?
So let me first answer first part of the question. Not necessarily. So if you add more legs, we can use the legs to improve speed. So there is a locomotion mechanism where the speed is a linear function of number of legs. More legs means higher speed. This is possible.
Based on what you showed, that depends on the gate, because if you're using leg versus body actuation, and
Correct.
just purely based on leg motion, introducing the redundancies would cost.
Correct. So that's actually reflects your first. So use computational intelligence. You got to choose between the agility and robustness. Yeah? You slow down. We would also like to choose to have those trade-offs, the spectrum between the agility and the robustness through the mechanical intelligence. So it's a broader spectrum, mechanical intelligence, computational intelligence, speed, agility. Think about it that way. We're filling the entire spaces.
All right, so we'll end Q&A there. Please join me in thanking Dr. Baxi Chong. Thank you so much for the wonderful presentation.